Students, in this video we are going to discuss about the basic signals. Okay, before going to this basic signal concept, we need to know why we need to study the basic signals and its properties. So considered a system, right? So the system can do any functionality, either it can do filtering operation or it can do convolutional operation, whatever the operation it may be. You need to know the input signal. You need to know the input, that is the input should be a known one. Okay, then only you can check whether the system functionality is working correctly or not. Okay, considered here I am going to perform an amplification operation, right? If I am amplification operation, consider the system is performing the amplification operation. Okay, so if the input is known, then only you can check whether the signal is amplified or not. Without knowing the input, without having the knowledge of the input, we may not able to justify our output, right? So for that purpose we are going to study these basic signals. Okay, so in this signals and system there are different basic signals are there, and these basic signals are used to study the system properties. Okay, and also these basic signals are elementary signals, and these allow us to better understand the properties of both signals and system. Okay, so here either the system may be a continuous time system or a discrete time system. The input may be a continuous time input or discrete time input. The output may be a continuous time or a discrete time. Okay, whatever the type of system, whether it is a continuous or discrete, you can use you can test the properties of both signals and systems by using this known basic signal. Okay, so for this purpose we are going to study this basic signals. In that, the first one is an impulse function. Okay, the first signal is an impulse function. Okay, so if we consider any signal, you can represent the signal in both continuous time and the discrete time. Okay, so first we will see impulse function. In that there are you can represent the impulse function in continuous time as well as the discrete time. Since these signals are known signal, it is having the mathematical relation, that is here the impulse signal is denoted by del of t, and in for continuous time it is del of t, and for discrete time it is del of n. So what is the property of this impulse is it will have the value only at time t equal to 0. Okay, so consider this is what your del of t and this is what your t. It will have the value only at the origin. Apart from that it won't have the value, it will 0. Now consider, I will draw it how I will differentiate this discrete and as well as the continuous time. This is del of n and this is n. Now consider a discrete time. Both are same, right? Here continuous time at time t equal to 0 you will have 1. At discrete time at n is equal to, this is what n is equal to 0, the value is 1. Now I can draw discrete directly because we are going to predict the value. We are going to predict the value at the n is equal to 0. Okay, so this is what the del of n. But in case of continuous, what will happen is this will have some width like this. Okay, so at t equal to 0 it is having some smaller width. Okay, so this is the continuous time representation of the del of t. This is the continuous time representation of the del of t. So in order to differentiate this continuous time and discrete time, here we are representing this with this impulse will have very smaller width. So how the width will be is here, when you integrate this, that is del of t dt is equal to 1. That is this area, if you integrate this area it will have 1, like so whatever it may be, so it should have the value 1. So that is the property of this unit impulse function. So how the width will be is, so consider the signal. Here I am representing del of t, here it is t. So now this width can be of broader if this with this tau, and this will be 1 by tau. Consider how will you find the area of the pulse, that is this width into height, right? So del into tau into 1 by tau, what you will get, you will get 1. So now if you reduce the tau, what will happen, this will increase, right? So now I am drawing the same impulse, okay, with smaller width. This width will this height will increase, right? So here this is tau and this should be 1 by tau. Okay, so you will get tau into 1 by tau is equal to 1. That is, the area under the impulse should be 1, whatever it may be, whether it may be a broader width or narrow width. Accordingly, the height and width should be adjusted so that the area under the impulse should be 1. So this is the thing you need to know. Okay, so this indicate that total area under the unit impulse is in unity. Okay, as this tau decreases, the width of the rectangular pulse shrinks and the height increases proportionally to maintain the unit area. So this should maintain the unit area. So here this is said to be an unit impulse function. Okay, so because the unit area is 1, so it is said to be an unit impulse function. Because in discrete time you can directly draw that because it is having value only at discrete time instant. So here the value is 0, at -1 -2 the value is 0, right? But in case of continuous time, so you should have some smaller continuous time pulses. Okay, so here in order to have this pulse, the area should be unity. How you can adjust the area? If the width is broader, the height will be smaller. If the width is smaller, height will increases in order to maintain the unity impulse. Okay, unity area. As this tau tends to 0, this pulse become a tall and a narrow spike with unit area and infinite amplitude. Okay, so the area under the impulse is called as strength or weight. So the area under the impulse is called it as, we can call this as strength or weight. Okay, an impulse with a strength, that is weight. Weight is nothing but the amplitude, right? Strength and weight. What is the strength of the signal? Here the strength of the signal is 1. So similarly, if the strength or weight of the signal is 1, then it is said to be a unit impulse signal. Okay, and this del of t is a theoretical tool used to understand the system and lead to the ideas that are used all the time in practice. The motivation of defining a function with these properties stems from the need to represent physical phenomena that happen in a short time duration. Example, consider a capacitor circuit in which there will be an instantaneous increase in voltage across a capacitor due to an extremely large current flowing for a very short time interval. The current flowing into the capacitor is modeled by an impulse function. So like that you can apply this impulse function to model any system, and also you can study the properties of the system using this impulse function. And also that here you may not you can also draw the impulse function like this, that is, this is of width tau and this is of this is of amplitude 1 by tau. It should not there is not a condition that it should occupy both positive and negative time duration. You can draw like this, right? So this is also an unit impulse with the tau and the amplitude 1 by tau. Like this also you can draw it. Okay, so this is also an impulse function with an area of unity. Next, we are going to study about the properties of the unit impulse function. First property is the product property. Y of t is equal to x of t into del of t. Okay, so if I am multiplying any signal, consider this is a real time signal like this, x of t, and I am multiplying with the impulse. What you are having, the impulse is having only width at this particular time. Okay, so I will get only the amplitude of this signal. Okay, so here what I will get is, I will get this signal because here the amplitude, when you consider this impulse, it is of unit amplitude, right? So you will get the value of like this. Okay, so you will get these portion alone. Okay, so because here there is no signal, here there is no signal, so when you multiply with this you will get the impulse function like this. Listen, don't bother about this 1 by tau into this amplitude. Okay, so what I here represent is the area under the impulse is unity. Now consider this case here. When this tau shrinks, what will happen? You will have an unit amplitude, right? You will have an unit amplitude del of t, right? So you will have an unit amplitude del of t. Okay, so this is at tau is equal to 0. When this case, when I multiply it by any signal, so what will be the resultant in this case? What will be the output? So I will get only value at this point. So consider this is the value, so I am getting only this value at this point. So any signal multiply with 1, consider the signal amplitude at this point is 5. Okay, when I multiply with this one, what I will get? I will get 0.5, right? So here this is what your y of t. So if you multiply an impulse with the corresponding signal, so you will get only the value that correspond to that where the impulse is present. Okay, so this is what the product property. Okay, now this impulse can also, we can shift it. Now if I want to perform t minus t naught, okay, so what I will do, consider this is t equal to t naught. At t naught somewhere else I will have the impulse, right? So I will have this peak. So this is del of t minus t naught and this is t. So when I multiplied a signal with this del of t minus t naught, so what I will get? I will get only value at t naught. So what is the value? I will get this amplitude at t naught. Okay, so this amplitude. So I will get the amplitude only at t naught. So this is what your y of t. So this y of t is equal to x of t into del of t minus t naught. Okay, so this is what the another thing. This is the, if I suppose if in a signal I want to consider this is a signal, so I want to find only the value at t equal to 5. Okay, so in this case what I will do? I will shift the impulse to t minus 5, right? I will shift the impulse to t minus 5. At 5 I will have the impulse, then I multiply with the corresponding signal, so that I will get the corresponding value at t equal to 5. So like that you can obtain the output if you want to obtain the output for a particular instant of time. Now similarly you can generate a train of impulses. What is the meaning of this is, consider, I will explain now. This is at time t equal to 0 you will have an impulse, right? Okay, so I need to have an another signal like this at time t equal to 1. Okay, so how you can obtain using an impulse? So this is what the original signal del of t, right? This is what the original signal del of t. So now how will you obtain this signal? So you have to shift at t equal to 1. So you will get del of t minus 1. When I add del of t and del of t minus 1, so consider that this one, you will get confused. So this is what at t equal to 0. Okay, next one, at 1 you will have an another impulse. Okay, so this is what del of t. Okay, this is what your del of t, this is what your del of t minus 1. So when I add these two signal, what I will get? I will get this signal, right? That is del of t plus del of t minus 1. Similarly, if I want to have at t equal to 2 then impulse, what I will do? I will add another signal at t equal to 2. Okay, so this is what del of t minus 2. Okay, so now I will add del of t minus 2 in this case. Like that you can generate the train of impulses at the positive side. Similarly, I need to generate an impulse at the negative side. What I will do? I will substitute del of t plus 1. That is t equal to minus 1 I am having. So I am adding this with del of t plus 1. Similarly, if I want to generate an impulse at t equal to minus 2, so here I will generate an impulse at t equal to minus 1. Similarly, if I want to generate the impulses at t equal to minus 2, what I will do? I will generate another signal. So like that I can generate a train of impulses. So I represent this signal, this represent up to infinity. So I represent this signal in general as del of t minus k into t naught. Okay, now consider here k equal to 0. When k equal to 0, you will get del of t. When k equal to 1, you will get del of t minus t naught. Okay, that t naught is 1 here. Like that you can write this, represent this signal with an impulse signal. Okay, so listen here, according to this I need to generate an pulse now. Okay, so what is the meaning? First substitute t equal to 0. When you substitute t equal to 0, in this case what you will get? You will get an impulse at this point. Okay, when you substitute k equal to 1, what you will get? T minus t naught at t equal to t naught, that is at t equal to t naught you will have an impulse, right? Then substitute 2 here, you will get t equal to 2 t naught. You will get an impulse at this point 2 t naught. Okay, similarly substitute the negative range minus 1. So minus 1 you will get positive, so you will get minus t naught here. So similarly here you will get minus 2 t naught. Like that you will generate an impulse. So for this expression you will have an impulse at t naught, 2 t naught up to 3 t naught. Similarly this extend in both negative direction. Okay. Okay, now when this impulse is multiplied by an signal, okay, now when this impulse is multiplied by a signal like this, okay, you are multiplying a signal by this is x of t and this is t and this is your impulse, okay, that is p of t here. So when you multiply with this impulse, so what you will get? Considered here you are having the impulse, right? So I will represent in this manner. So this is what the impulse you are having, that is amplitude 1. Yes, so t naught, 2 t naught, this is what minus t naught, minus 2 t naught. So when you multiply x of t with this, so what you will get is you will get the these amplitude alone, right? This point, this amplitude, this like this. Okay, so like this. So this is what your t naught, this is minus 2 t naught plus 2 t naught. So I will have only the amplitude of this at this point. So I won't have this signal. So I will have the amplitude of the corresponding signal. Okay, so here a continuous time signal is converted into a discrete time signal. This is what the continuous time when you multiply with the that is train of pulses. So the output y of t is equal to x of t into p of t. The output will be like this. You will get only this value at this point. Okay, so this a continuous time signal is converted into a discrete time signal. So far we have seen the only the product property. Next one is shifting property. We have already discussed that is any signal multiplied with the del of t and we are integrating it, you will get that value at that particular insert. Del of t you will have value at time t is equal to 0, so you will get x of 0. Similarly here you will have x of t when you multiply it by t minus t naught into dt, you will get value at this t naught. Okay, because you will have an impulse at t equal to t naught. Okay, so this property is known as the shifting property. Okay, another next property is scaling property. Third property is scaling property. So scaling property also we have discussed that the area under the unit impulse should be 1, right? Okay, so if this is tau and this is 1 by tau, that is area under the unit impulse should be 1. When this tau increases, this width will be reduced, okay, in order to maintain the unity. Okay, so this is the scaling property of an unit impulse signal. What is the meaning of it is, if you are scaling del of at, you need to divide this by 1 by del of t in order to maintain the unity, that is for a greater than 0.